Hello everyone. In this session, we will solve one more problem on the sinking of continuous beam. So, how to deal with sinking problems when we are using Kani's method as the method for the analysis. So, in this session, we will try to analyze a continuous beam with one support sinking. We will analyze this beam using Kani's method and we will draw the shear force and bending moment diagrams. Okay. So, the problem what I have chosen today, it is the similar problem which we have solved, but in that case I have not considered the sinking. Here I am considering the sinking of one support. It is a 3-span beam. The beam is of 3-span. The support A, it is fixed in the nature. Support B, simple. Support C, it is also simple in the nature, and the support D is also simple in the nature. On this beam, we have a load. On span AB, the load is of UDL in the nature and the magnitude is 20 kilonewtons per meter. Similarly, on a CD span also we have a UDL of magnitude 20 kilonewton per meter. On span BC, we have a concentrated load of magnitude 50 kilonewton, but this 50 kilonewton is not acting exactly at the center, it is acting at some distance. So, this distance, that is from A, the point load is at a distance of 3 meter, from C it is at a distance of 2 meter. The span AB, it is about 6 meter, and the span CD, it is about 4 meter, right. So, for this case, the variation I value is a constant. So, there is no variation in the I value. So, the span AB is of 6 meter, which carries a UDL of 20 kilonewton. The span BC is of 5 meter, which carries a concentrated load of 50 kilonewton at a distance of 3 meter from B. Similarly, the span CD, it carries a UDL of 20 kilonewton per meter and its span is about 4 meter. And the important thing is the support B, it is sinks by 10 millimeter. That is, the support point B, it is sinking down by 10 millimeter from its original position. So, when a support is sinking, then obviously the development of bending moment will be something different. So, we have to observe just because of this 10 millimeter sinking, how the development of the shear force and bending moment pattern will change, that we need to observe. So, whenever we are using sinking, we need a value of EI, that is modulus of rigidity. So, here the modulus of rigidity is 2.4 into 10 to the power 10 kilonewton meter square. The EI value, modulus of rigidity value is given. So, we have to make use of this EI value in the analysis. So, our aim in the problem is to analyze the beam shown in figure by Kani's method, and we need to draw SFD, shear force diagram, and BMD. So, our ultimate aim is to draw the SFD and BMD, right. Okay. So, let me start with the analysis. So, we have to go by step solution. Step number 1, So as we all know, the step number 1 is to determine the fixed end moments. So we have to calculate the fixed end moments for all the 3 spans. Okay. So let me start with the first span, that is MFAB. MFAB. So now see here, the support B, it is sinking. The support B is sinking by 10 millimeter. Because of this sinking, because of support sinking B, the span AB and BC, they are both are getting affected. See, for example, this is span AB and this is span BC. If support B, this junction, if it is sinking, then you can see both span AB and BC, they both are getting affected. The span AB, it is rotating in the clockwise direction because of sinking, and span BC, it is rotating in the anti-clockwise direction because of the same support sinking. It means, what I am trying to say is, the delta value, the sinking value for span AB, it is positive, and the sinking value delta for span BC, it is negative. Right. Now, so as the load is UDL on the span AB, it is WL square by 12 is the formula to determine the fixed end moments. But apart from the sinking, apart from the external load, the span AB, it is also affected by the sinking. So the sinking has to be considered here itself. While calculating the fixed end moments, we need to consider the effect of the sinking also. So what I will do, I will consider the sinking also. We all know that the sinking effect is considered from the formula minus 6 EI delta by L square. This is the formula to consider the effect of sinking, that is the moments developed due to sinking. This part will be considered. Okay, right. So here the load is 20 kilonewton per meter. So 20, span is 6 meter, so it is 6 square divided by 12 minus 6, EI value is given, so it is 2.4 into 10 to the power 10 into delta. Delta is positive. For span AB, it is positive. See here, as the support B is sinking down, let us say something like this, the position of the beam, it is something like this. So it means the entire beam is rotating in the clockwise. So because of this, here we consider the delta as positive, whereas the span BC, it will be modified or it will be deformed in this fashion. So here the delta, it will be negative. For span BC, the delta value is considered as negative. So here I will consider the delta value as positive. So the deflection or the deformation is about 10 millimeter. So 10 millimeter, it means 10 by 1000. This is about 0.01 meter. The delta value is 0.01. So it is 0.01 meter divided by L. Span is 6 meter. So it is 6 square. So this we will get, this is minus. So it is here, we will get it as minus 60, then minus 40. So this is yields to minus 100 kilonewton meter. So this is a fixed end moment for this span AB. Now similarly, we need to determine the fixed end moments for this span BA, that is MFBA is equals to, it is plus WL square by 12 then minus 6 EI delta by L square. So here it is plus W is 20 into L is 6, so it is 6 square by 12 minus 6 into EI. EI value is given, it is 2.4, 2.4 into 10 to the power 10 into the delta value. The delta value is also known, that is 0.01 divided by L square. L is 6, so it is 6 square. Right. So we will get plus 60 minus 40. So MFBA will be, it is plus 20 kilonewton meter. MFBA is plus 20 kilonewton meter. So this is the fixed end moments for the span AB. Similarly, we need to work out for the span BC, that is MFBC is equals to, so here on the span BC we have a concentrated load which is not at the center, eccentric concentrated load. For that we need to use minus WAB square by L square as the formula to determine the fixed end moments. But the span BC, it is affected by the sinking. So we need to consider the sinking component into the calculation. So here minus 6 EI into delta by L square. So this component we need to consider into the calculation. See, now here minus W is 50 kilonewton, 50 into A is 3 meter, B is 2, so it is 2 square divided by 5 square minus 6 into EI. EI is 2.4 into 10 to the power 10 is the EI value into delta. Delta is 0.01. Here for span BC, as due to the sinking the entire span is rotating in the anti-clockwise direction. So the delta value for span BC, it has to be considered as negative. It means here the delta value is 0.01 whole divided by 5 square. So this yields to a value MFBC minus 24 minus of minus, it will be plus 57.6, which gives you 33.6 kilonewton meter as the fixed end moment at B, that is MFBC. Similarly, we have one more MFCB. MFCB is equals to, it is plus WA square B by L square minus of 6 EI delta by L square. Right. So thus it is plus W is 50 kilonewton, A value is 3, so it is 3 square into B is 2 whole divided by 5 square minus the same thing 6 into 2.4 into 10 to the power 10 into minus 0.01 whole divided by 5 square. This gives you plus 36 plus 57.6, which yields to plus 57.6, it is 93.6 kilonewton meter as the fixed end moments. So lastly, we have the span CD, which is very simple because this span is not affected by the sinking of the support B. So as usual, we need to calculate the fixed end moment for the span CD. MFCD is equals to minus WL square by 12. So minus of W is 20 into span is 4. So it is 4 square by 12, which yields to a negative value of minus 26.61, 26.67 kilonewton meter. And lastly, MF DC is equals to, it is plus WL square by 12, which gives us plus 20 into 4 square divided by 12 equals to plus 26.67 kilonewton meter, right. So these are the fixed end moments for the span AB, BC and CD. So here what we have done, we have calculated the fixed end moments by considering the external loads along with the effect of sinking. But as per the Kani's method, whenever we are dealing with one of the end support as either hinge, roller or simple support, then we have to modify the fixed end moments for that particular span. We have to modify the fixed end moments. So here you can see the support D, it is simple in the nature. It means for span CD, we need to modify the fixed end moments. So let us modify the fixed end moments. Modified fixed end moments. It is only for span CD. Only for span CD we are modifying the fixed end moments, as the end D, it is the simple in the nature. Now, as end D it is simple in the nature, we know that the final end moment must be 0. It means the MCD has to be 0. How MCD will become 0? We know that MDC must be 0. To become MDC, MFDC has to be 0. MFDC, but as per our calculation, MFDC it is plus 26.67. So it is 26.67. To make this 0, what I need to do? I need to apply an equal and opposite moment, that is minus 26.67. Then it will becomes 0, right. So to make this 0, what we are doing? We are applying an equal and opposite moment here. So whenever we are applying an additional moment to make something 0, so half of that moment has to be transferred to the other end of the same moment. Means when I am applying some moment here, half of that will be transferred here. It means MFCD will be modified. The existing MFCD is, it is minus 26.67, minus 26.67. Then half of this moment we are transferring here, that is minus 26.67. So this will be modified, that is M dash FCD, it is equals to, it is about minus 40 kilonewton meter. So these modified fixed end moments we need to use in the calculation, not the actual, because, and you should remember why we are modifying this, right. Okay. So once we modify these fixed end moments, then we can go for the step number 2, that is the calculation of relative stiffness and the rotation factors. Step 2, relative stiffness and rotation factor. Right. To to determine the relative stiffness and the rotation factors for the different components, different members, we have to prepare the table. So, I hope you all know how to prepare the table, right. So, here let us note the joints first, then we have to notify the members, then we have to work out the relative stiffness, that is the value of K. Then we have to determine the summation of K, that is total stiffness, then distribution factor, then the rotation factor. U is equals to minus half of distribution factor. Okay. So, here from the given loading diagram, what I can understand is there are two intermediate supports, one is B and another one is C. For these two joints, we need to calculate the rotation factors. So, let us note those two, one is B, another one is C. At B joint, we have two members, one is BA, another one is BC. So, BA and BC, these are the two members at joint B. Similarly, at joint C, we have two more members, one is BC, another one is CB, another one is CD. CB and CD, these are the two members at joint C. Now, for each member, we need to calculate the relative stiffness value depending upon the far end condition, right. So, now see, for BA member, A is far end and it is fixed in the nature. So, the relative stiffness is I by L, right. So, I value is not given, it means I value is I, L is 6 meter. So, it is I by 6. I by 6 gives you 0.17 I. 0.17 I, that is the relative stiffness for the member BA. Similarly, for BC member, C is the far end condition. Far end here, as per the given loading diagram, it is an intermediate support and all the intermediate supports are assumed as fixed. So, for this also it is I by L. So, it is I by L is 5 meter. So, it is 0.2 I, right. So, the total K, it is 0.37 I is the total relative stiffness at B joint. Similarly, for C joint, we have two members, one is CB and another one is CD. For CB member, B is the far end and it is intermediate support. It is assumed to be fixed in the nature. So, the relative stiffness is I by L. So, I is I, L is 5 meter. So, this is also 0.2 I. And the CD, in the CD member, D is far end and T is simple in the nature. So, whenever we are dealing with a far end, either simple hinge or roller, the relative stiffness is, it is 3I by 4L. So, here it is 3I by 4L. So, 3 into I value is I and L is 4 into 4, right. This gives you 0.19 I, 0.19 I. So, this total it will be 0.39 I, right. Now, based on this, we can easily estimate the distribution factors. So, distribution factor is equals to, we all know, it is K by summation of K. For BA member, it is 0.17I divided by 0.37I gives you 0.46. 0.46 and 0.2I divided by 0.37I gives you 0.54. 0.54, right? And similarly for CB member, it is 0.2I divided by 0.39I gives you 0.52. 0.52 and here it is 0.19I divided by 0.39I gives you 0.48. 0.48. So, these are the distribution factors. With the help of the distribution factors, we can easily work out the rotation factors. Rotation factor is equals to, it is minus half of the distribution factor. So, minus half of this, it is minus 0.23, minus 0.27, here it is minus 0.26, minus 0.24. These are the rotation factors, right? These factors we need to use in the calculation of the rotation contributions, right? That is in the step number 3. Okay. So, let me start with step number 3. In the step number 3, that is Kani's table. So, we need to write the Kani's table. In the Kani's table, what we need to do is, we need to represent the members as it is. We have to replace the joints by boxes. Okay. So, here I am replacing the joint B by a box. Similarly, I am replacing the joint C by a box. Joint D, that is the end D will remain same. So, this is end A, this is B joint, this is C joint and this is D, right. So, in these boxes we need to write one more small boxes and join the diagonals. Here also I have to join these diagonals. So, this is the representation of the Kani's table. Okay. So, here at the top of the member we need to write the fixed end moments MFAB, MFBA and similarly. So, as per our calculations MFAB, as per our calculations the fixed end moment, that is MFAB, it is minus 100. So, I will write that as it is minus 100. MFBA, as per our calculation it is plus 20, right. I will write these as it is. MFBC, it is minus 33.6, minus 33.6 and MFCB, it is plus 93.6, 93.6. MFCD, here we have modified, we have to use the modified fixed end moments. So, modified fixed end moment MFCD, it is minus 40 and MFDC, it is 0, right. So, we have to use these modified equations, modified values in the Kani's table. And as per the step number 2, we have calculated the rotation factors, those I need to represent here. Minus 0.23, minus 0.23, minus 0.27. So, these are the rotation factors for member BA and for BC. Similarly, for member CB and CD, it is minus 0.26 and minus 0.24. So, these are the rotation factors, right. Now, once we estimate the rotation factors, our next duty is to calculate the rotation contributions, that is M dash AB, M dash BA, M dash BC, M dash CB, M dash CD and M dash DC. These are the rotation contributions, but Kani has clearly said that it is not necessary to calculate the rotation contributions at the ends. We have to calculate the rotation contributions only for the intermediate joints, that is for joint B and joint C. In this case we need to do, right. So, here we need totally 4 rotation contributions. One is M dash AB, M dash BA, M dash CB and M dash CD. For these 4 members we need to calculate the rotation contributions. So, let us start the cycle. As per the cycle 1, okay, before that I will write the general formula. Rotation contribution M dash is equals to, it is rotation factor U into the algebraic sum of fixed end moments MF plus the algebraic sum of far end rotation contributions. So, this is the formula, general formula to calculate the rotation contributions. So, here for the first cycle, if I want to know how much is M dash BA, right. So, M dash BA is equals to rotation factor U. Rotation factor here is minus 0.23 into the algebraic sum of fixed end moments. So, here we are not yet estimated the algebraic sum of fixed end moments. So, how much is the sum of fixed end moments at B joint? At B joint we have 2 members, one is BA and another is BC. For these 2 members, if I take the sum of the fixed end moments, what is the net value? So, net value, that is plus 20 minus 33.6. So, that gives you I think this is a positive value, plus 33. So, total it is 53.6. It is 53.6, and at joint C it is about 53.6 there also, plus 40. Okay. So, both are same here, 53.6 and 53.6, right. So, the rotation factor here is, sum of fixed end moment is 53.6 plus the far end rotation contributions. So, for joint B, which are the far end rotation contributions? See here, for joint B, for this joint, M dash AB and M dash CB, these 2 are the far end rotation contribution. Means whenever I am calculating the rotation contributions for this joint, that is M dash BA and M dash BC, I need to use M dash AB and M dash CB as the far end rotation contributions. And similarly for C joint, I have to use M dash CB and M dash DC, M dash BC and M dash DC as the rotation contributions for the C joint. That is, whenever I am calculating the M dash CB and M dash CD, I need to use M dash BC and M dash DC as the far end rotation contributions. Now, here for this, that is while calculating the M dash BA, M dash AB and M dash CB. So, this is 0 and this is we don't have any value, so initially I will take it as 0. So here it will be 0 plus 0. This gives me a value of minus 12.33. It is 12.33 kilonewton meter, which I am going to write here, minus 12.33. Now similarly for this, that is m dash BC, m dash BC is equals to minus rotation factor. So rotation factor is minus 0.27 into the algebraic sum of fixed end moments 53.6 plus far end rotation moments, they will be 0 and 0. This gives me a value of minus 14.47, minus 14.47 kilonewton meter. So now I have calculated the rotation contributions for the joint B. So which we have to represent here. This is minus 14.47. Go to the next joint. So for the joint C, we need to again calculate the rotation contributions, that is m dash CB and m dash CD. So m dash CB is equals to rotation factor. So here rotation factor is minus 0.26, minus 0.26 into the algebraic sum of fixed end moments. Again it is 53.6 plus far end rotation contributions. Now for the C joint, which are the far end rotation contributions? M dash BC and M dash DC. How much is M dash BC here? It is minus 14.47. So it is here minus 14.47 plus 0. Plus 0, here M dash DC is 0, right? So if you work out that, you will get minus 10.17. You will get minus 10.17. And M dash CD. If I calculate M dash CD, the rotation factor is minus 24, minus 0.24 into the fixed end moment is 53.6 minus 14.47 plus 0. This gives me a value of minus 9.39. Minus 9.39. These are kilonewton meter. So let me represent these two in the diagram. Here it is minus 10.17 minus 9.39. So this completes one cycle. Similarly, we need to keep on repeating these cycles, that is we need to keep on repeating calculation of the rotation contributions at the B and C joints until we get the same rotation contribution values. See, in the next cycle, as we discussed earlier also, only these things will change. The rotation factor and the algebraic sum of fixed end moments, they will remain same. The rotation contributions will be changing. Now for the second cycle, if I want to calculate the rotation factor m dash BA, so it is rotation factor into fixed end moment plus the far end rotation contributions. M dash AB 0 plus m dash CB. Here it is, now we have a value. Initially I have taken it as a 0, but now in the second cycle we have a value that is minus 10.17. So this will be minus 10.17. That gives you a value of minus 10. This gives you 10.00 and m dash BC it is 0 minus 10.17. This is also gives you minus 10.00 kilonewton meter. No, sorry, this is not 10.00. This is 11.73. 11.73. So that I am going to represent here minus 10.00 11.73. So these are the next cycle rotation contributions for the joint B. Now similarly if I repeat it for the joint C, then these two will remain same, that is minus 0.26 into 53.6 minus 11.73 plus 0. And here also it is minus 11.73 plus 0. This gives us a value of minus 10.89 kilonewton meter and minus 10.05 kilonewton meter. Here it is minus 10.89 and here it is minus 10.05. You can see the values, they are close. Now if I go for one or two more cycles, then obviously I may get the same values. Let us see the cycle 3. In the cycle 3 also again everything will remain same, only these far end rotation contributions they will change. Okay. Here you can see for m dash BA it is rotation factor minus 0.23 into algebraic sum of fixed end moments plus 0 minus it is this value, that is m dash CB, it is minus 10.89. That gives you a negative value minus 9.82 kilonewton meter and m dash BC it is minus 10.89. That gives you a negative value minus 11.53 kilonewton meter. So if I represent those here 9.82 and 11.53, you can see there is a reduction in the difference. And for the next joint, that is for joint C, m dash CB rotation factor into the algebraic sum of fixed end moments plus the far end rotation contributions, that is 11.53 plus 0 minus 11.53 plus 0. These two gives you a value of minus 10.94 kilonewton meter and minus 10.10 kilonewton meter. So here it is minus 10.10 minus 10.94 and minus 10.10. So now you can see the third cycle. In the third cycle again the difference is very less. Might be in the next cycle you may get the exact same values. So let us go for the next cycle. In the next cycle it is 0 minus 10.94 0 minus 10.94. So that gives you a value of 9.81 minus 9.81 kilonewton meter and minus 11.52 kilonewton meter. So that I am going to write here minus 9.81 and minus 11.52. For the joint C, it is minus 11.52 plus 0, minus 11.52 plus 0. So these two gives you the same values, that is minus 10.94 kilonewton meter and minus 10.10 kilonewton meter. So it is minus 10.94 minus 10.10. Now you can see here these two values they have repeated and these two are also very close. It means if I go for the next cycle, then obviously in the next cycle the value will be exactly similar. So based on this understanding, we can finalize these are the final rotation contributions for the joints. So we can use these final rotation contributions to calculate the final end moments, right? Okay. So based on this, let us calculate the final end moments, that is step number 4. Step number 4, final end moments. Final end moments. So here final end moments MAB is equals to, it is MF AB plus 2 times of the M dash AB plus 1 times of the M dash BA. So MF AB, for AB member MF AB is minus 100, it is minus 100 plus 2 times of M dash AB, M dash AB it is 0 plus M dash BA. As per our calculation, the M dash BA it is minus 9.81, which gives you 109.81. It is gives minus 109.81 kilonewton meter as the final end moment. Now, if I repeat it for the other moment, that is MBA, it is MFBA plus 2 times of the M dash BA plus 1 times of M dash AB. That is, as per our calculation, MFBA it is plus 20 plus 2 times of the minus 9.81 plus 0. This gives you a value of plus 0.38 kilonewton meter, plus 0.38 kilonewton meter. Now similarly repeat it for the other span, that is MBC, you will get at minus 0.38 kilonewton meter and MBC you will get MCB as plus 60.2 kilonewton meter, MCD as minus 60.2 kilonewton meter, MDC you need to write it as 0. Don't use the formula to calculate the final end moments, because in the initial step while calculating the fixed end moment itself we have made it as 0. So don't use the formula to calculate the fixed end moments. Straight away write the MDC as 0. The final end moment at a D, MDC is equals to 0. Right? Okay. So next, once we calculate these, so we need to represent them into the loading diagram. MAB, as per our calculations, we got it as minus 109.81. Minus indicates anticlockwise moment. So here I am going to write a negative anticlockwise moment. 109.81 kilonewton meter. At B joint, see here we got 0.38 as clockwise moment and minus 0.38 for BC. So, one is clockwise and this is clockwise and this is anti-clockwise. Its magnitude is 0.38 kilonewton meter, right. And for C joint, you can see MCB is plus and MCD it is minus 60.2. So, plus indicates it is clockwise, minus indicates anti-clockwise. So, it is 60.2 kilonewton meter, and at D the moment is 0, no need to represent anything. Okay. Okay. So, once we have the final end moments, our next duty is to calculate the support reactions and the maximum bending moments. Let me do that under the step number 5. Step 5, support reactions and maximum bending moments. Under this heading, let me do the remaining calculations. So, here to calculate the support reactions and the maximum bending moment values, we need to draw the free body diagram of each span. So, let me start with the span AB. If I draw FBD of span AB, then you can see on the span AB we have a UDL, and let me consider the supports AB. It has got a UDL of magnitude 20 kilonewtons per meter. Okay. So, apart from this, it has got two moments. Okay. So, one is 109.81 kilonewton meter and the other one is just 0.38 kilonewton meter. So, let me call this a support as RAB and this as RBA. The span is 6 meter. Okay. So, for this we need to calculate RAB and RBA, the support reactions, and also in the span we need to calculate the maximum bending moment. So, for that what I will do, I will impose the moment condition about A and equate it to 0. So, if I take the moment of all the forces about A, then this 20 kilonewton creates a clockwise moment. So, it is 20 into 6 into acting at a distance of 6 by 2 minus we have this anticlockwise moment 109.81, then we have this clockwise moment plus 0.38, then plus minus this support reaction, it is creating an anticlockwise moment. So, minus RBA into 6 equals to 0. So, if I solve this equation, I will get the value of RBA, that is reaction at B, RBA as 41.76 kilonewtons. So, this is the support reaction at A. Similarly, I need to impose the one more equilibrium condition, that is algebraic sum of vertical forces must be equals to 0. If I impose this equilibrium condition, then I will get another support reaction RAB. So, here you can see RBA and RAB, they are acting vertically upwards. So, RAB plus RBA minus this UDL is acting vertically downwards. So, it is 20 into 6 equals to 0. Here in this equation we have the value of RBA. If I substitute that, we will get the value of RAB as 78.24 kilonewtons, right. Okay, so these are the two support reactions, but we need to calculate the maximum bending moment in the span AB. How to do that? So that can be done with the help of the shear force diagram. If I draw the shear force diagram, from the shear force diagram I can make out that a point where the shear force is 0, and we all know that wherever the shear force is 0, at the same point the bending moment is maximum. So what I need to do here is, with the help of the support reactions values, I need to draw the shear force diagram. From the shear force diagram, locate the point where the shear force is 0. Okay, so let me do that. So I will draw the shear force diagram. Okay, so here at A we have a reacting component RAB which is acting vertically upward. So I will take the shear force diagram or shear force line to vertically upwards. It has 78.24. From here to here, that is from A to B, we have a UDL which is acting vertically downwards. So plus 78.24 minus 20 into 6, that gives you a negative value of minus 41.76. So minus indicating a negative, I will take the shear force diagram on the negative side. So this is minus 41.76. But at point B we have another reacting force which is acting vertically upwards. So minus 41.76 plus 41.76, it is 0. So from here I have to take the line vertically up. So this will be 0 point. So now you can see this is a point where the shear force is 0. So let me call this as, let me call that point as point E. This is a point E. So let us say this is at a distance of x. So if that is x, so this will be 6 minus x. Okay. So I need to determine the point where the shear force is 0. Okay. So what I will do here, I will impose the symmetric triangle concept. Then I can write x by 78.24. This ratio must be equals to 6 minus x by 41.76. So here if I work out, then I will get x as 3.91 meter. It means at a distance of 3.91 meter from point B, the value of shear force is 0. Now from this, what I can say is, at a distance of 3.91 meter from the point A, the bending moment is maximum. So at that location we need to determine the bending moment. Therefore bending moment at E, that is ME, if I calculate the left portion of the point E, so this portion for the calculation purpose, then on the left side we have a reacting force RAB which is creating a clockwise moment. So it is 78.24 into x, x is 3.91, minus we have an anticlockwise moment 109.81, minus of the UDL which is on there, on this portion it is creating an anticlockwise moment. So it is minus 20 into 3.91 into 3.91 by 2. So if you work out this equation, you will get the maximum bending moment at point E as 43.22. ME as 43.22 kilonewton meter. So this is the fixed end moment, sorry, this is the maximum positive bending moment at point E, right? Okay. Similarly, we need to repeat this procedure for the second span and for the third span. FBD of span BC. Now here you can see on span BC we have a concentrated load of magnitude 50 kilonewton, which is at a distance of 3 meter and the other distance is 2 meter. Apart from this, on the span BC we have the end moments. On the left side we have an anticlockwise moment of 0.38 kilonewton meter, and on the right side we have a moment of 60.2 kilonewton meter. So because of this, we need to calculate the support reactions RBC and RCB. These are the two support reactions we need to calculate, and also as on the span BC a concentrated load is acting, so we can directly say that under the concentrated load the bending moment will be maximum. A, B, C, D, E. So let me call this as F. That is, we need to determine the bending moment at F. Okay. To calculate the maximum support reactions, I will impose the equilibrium conditions on this. Okay. So here if I impose the moment condition at B and equating it to 0, then this 50 kilonewton creates a clockwise moment. So it is 50 into 3. Then we have an anticlockwise moment, so minus 0.38, plus we have a clockwise moment 60.2, minus this reacting force creates an anticlockwise moment, so it is RCB into 5 equals to 0. So from here we will get the RCB as 41.96. We will get the 41.96 kilonewtons acting vertically upwards. So we have got one support reaction, that is RCB. So we need to calculate one more support reaction RBC by imposing the second equilibrium condition. So here let me impose the summation of vertical forces must be equals to 0, this equilibrium condition. So RBC and RCB, they are acting vertically upwards. RCB plus RCD minus of this load is acting, that is 50 kilonewton is acting vertically downwards, equals to 0. So here if I substitute, so this is R, this is RBC. If I substitute the value of RBC, I will get substitute the RCB value, I will get RBC as 8.04 kilonewtons. This is also acting vertically upwards. Now we need to calculate the maximum bending moment here under the point load. So let me consider MF in the left portion. If I consider the left portion, on the left side we have a reacting component RBC, that is 8.04 into its distance is 3 meter, minus we have an anticlockwise moment, so it is 0.38. So MF, it is about 23.72 kilonewton meter. So this is the maximum bending moment under the concentrated load. Okay. Right. So this is about a span BC. Now similarly we have to repeat the procedure for the span CD. Okay. Let me do that. So this is a free body diagram of span CD, where we have a UDL of magnitude 20 kilonewtons per meter. We have an end moment of 60.2 kilonewton meter. So there is no moment at the D point, as it is simple in the nature. C, D. So here we need to determine the reacting component RCD and RDC, right. Again, to do this also, I am going to impose the equilibrium conditions. So here let me impose the moment condition at C equating to 0. So if I impose this condition, that this 20 kilonewton creates a clockwise moment. So it is 20 into the span is 4 meter. So it is 4 into acting at a distance of 4 by 2 minus this anticlockwise moment 60.2 minus of this reacting component RDC. It is also creating an anticlockwise moment. So it is RDC into 4 equating it to 0. From this we will get the value of RDC as 24.96 kilonewtons acting vertically upwards. Similarly, impose one more equilibrium condition, that is summation of f of y is equals to 0. So RCD and RDC, these two are acting vertically upwards. RCD plus RDC minus this UDL is acting vertically downwards. So it is 20 into 4 equating it to 0. If I substitute the value of RDC here in this equation, I will get the value of RCD. So RCD is equals to, we will get RCD as 55.05 kilonewtons acting vertically upwards, right. Okay. So we got the values of support reactions. With the help of these support reactions, we need to draw the shear force diagram. Why? Because we need to know the point where the shear force is 0. From that we will be able to calculate the maximum bending moments. Okay. So we have discussed how to draw the shear force diagram many times. So I will draw the shear force diagram directly. So this value is 55.05 and this value is 24.96. So let us say this is a point where the shear force is 0. Let us call this as A, B, C, D, E, F, G. Let us call this as point G. Let us say G is at a distance of x and this distance is 4 minus x. Now here I can write x by 55.05. This ratio must be equals to 4 minus x by 24.96. From this we will be able to determine the value of x as 2.75 meters. So at a distance of 2.75 meter from C, the shear force is 0. So exactly at the same point we need to determine the bending moment, that is mg. Mg is equals to, if I take the left side, so left side we have a reacting component RCD which is creating a clockwise moment. So it is 55.05 into the x is 2.75 minus this moment 60.2 minus of 20 into 2.75 into 2.75 by 2. This gives you mg as 15.56 15.56 kilonewton meter, right? Okay, so these are the values. So now with the help of these values we need to draw the shear force and the bending moment diagrams. Okay, let us see. Okay, so here I will draw the projection lines so that it is easy for me to draw the shear force and bending moment diagrams. Okay, so I have drawn the projection lines. With respect to these projection lines, let me draw the shear force and bending moment diagram. Let us consider the datum line. Let us say this is the datum line for the SFD. Okay, so for the span AB, at A we have a reacting component RAB, which is 78.24. So I will represent this by taking line vertically up, 78.24 kilonewton. Soon after the point A till point B, we have a UDL which is acting vertically downwards. So 78.24 minus that UDL gives you a negative value, that is minus 41.76. Minus 41 point means I have to mark it on the negative side. So this is 41.76. Because of the UDL, the variation is linear. So here I have to draw a line linearly. Okay, looking like parabolic. Okay, right. Now at point B we have one more reacting component, that is RBA. So RBA, it is plus 41.76. So this is minus 71.6 plus 71.56, it is 0. So I have to take this line vertically up. So it is 0. And at point B we have one more reaction, RBC. So as per our calculations, RBC, it is 8.03, very less value. So as it is a positive, I am going to take it as vertically upwards. It is just about 8.03 kilonewtons, right? But from B to this F point, that is till the concentrated load 50 kilonewton, we don't have any other loads. So I have to maintain the line constant, right? So at F point we have a vertical load which is acting vertically downwards. So here this 50 kilonewton concentrated load, as it is acting vertically downwards, so it is minus or negative, plus 8.03 minus 50, that gives you a negative value of minus this is 804, that gives you a negative value of 41.96. So it means somewhere here I have to mark it, it is about 41.96. So the line will be vertical, right? From F to C we don't have any load, so it is a constant. But at C we have one more reacting components which is acting vertically upwards, that is RCB. So RCB is, it is plus 41.96, minus 41.96 plus 41.96, it is 0. Okay. If I come to the span CD, at C we have a positive reacting force, that is a reacting force which is acting vertically upwards, RCD. RCD, it is about 55.05. So as it is a positive value, I am going to take the line vertically up. It is about 55.05 kilonewtons. From C to D we have a UDL which is acting vertically downwards. Because of this UDL we will get a negative shear force on the end D. 55.05 minus 20 into 4. So you will get a negative value of minus 24.96. You will get minus 24.96 kilonewton. But at point D we have a reacting component RDC. So RDC is a positive as it is acting vertically upwards. So that is 24.96. This is in minus 24.96 plus 24.96 gives you a 0. So here it will end at this point. The line which is there above, it is positive shear force, the area above the datum is positive shear force, below it is negative shear force. Positive, negative, positive, negative. So you can just hatch it. Right. So this is very brief about the shear force diagram. Similarly, we need to draw the bending moment diagram. Okay. So let us say this is the datum line for the bending moment diagram. Okay. For span AB, let us say A is on the left side and B is on the right side. So left side we have an anticlockwise moment. So left side anticlockwise is negative. So I will show that is vertically, on the negative side, 109.81 kilonewton meter. On the right side we have a clockwise moment. So right side clockwise is again negative. So that also I need to represent on the negative side, but here value is just 0.38. So I will be representing very close to the datum line, 0.38 kilonewton meter. Okay. But in between the span, that is in between AB, we have a point E. At point E the bending moment is positive and it is maximum. So that value as per our calculation it is 43.32. So here I am going to mention one more point here, 43.22 kilonewton meter, which is a positive bending moment. Because of the UDL, the variation will be parabolic in the nature. Sorry, I think I have represented this wrong. So here it has to be 0.38. Okay. So this is parabolic in the nature. Okay. Right. So now moving on to the second span, that is for BC. So let me consider B is on the right side and B is on the left side and C is on the right side. Left side we have anticlockwise moment, it is negative as represented. Right side we have a clockwise moment, so right side clockwise is negative. So it means I have to represent it on the negative side, that is 60.2 kilonewton meter. But in between these two we have concentrated load. So at concentrated load we will have the maximum positive bending moment. As per our calculation it is 23.72. So let me represent that is somewhere here, 23.72 kilonewton meter. So because of the concentrated load, the variation in the shear bending moment diagram will be linear. Right. Coming to the last span CD, so C is on the left side and D is on the right side. Left side we have an anticlockwise moment, so it is as represented. Right side we don't have any moment, it means it is 0, so exactly in the datum line. But at point G we have a positive bending moment, that is mg is equal to 15.56. So somewhere here I need to represent it as 15.56 kilonewton meter. So because of the UDL, the variation will be parabolic in the nature, right? So this is a negative bending moment, it is positive bending moment, this is negative, this is positive, this is negative, and this is positive, right? So this is a bending moment diagram. So here one thing can be observed, as we have already solved this problem without considering the sinking, and this is we have solved by considering the sinking of only one support, that to adjust 10 millimeter. Now you can observe the difference in the variation of the bending moment values. So a small sinking of any support affects the structure in a bigger way. So from this what we can understand is the sinking of any supports or any structure, it is not that good in the structures. If any support is sinking, then it affects a lot to the structures. Okay, thank you.